Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on RBS. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Daniel Zhang, Senior Scientist at EAG Laboratories.
Welcome to the Smart Chart webinar series. Today, we'll be talking about RBS, or Rutherford Backscattering Spectrometry. My name is Daniel Zhang. I'm a senior scientist at Eurofins EAG. I have just over 14 years of experience doing RBS. During this time, I've had the pleasure of observing most of the elements of the periodic table. I have a background in the semiconductor industry in materials development and equipment. This is what we will cover in today's webinar. We will start with an introduction to EAG, then proceed to the SMART chart, which is a chart which brings together the analytical techniques. We will look at the fundamentals behind RBS. After that, we will look at some examples of RBS analysis. We will finish by summarizing the strengths and limitations and discuss other techniques that are complementary to RBS. EAG Labs has multiple locations in the United States, Europe, and Asia. We have over 600 highly educated employees using many techniques at over 20 locations, serving over 4,000 clients in 50 countries. This company has made a considerable investment over the years in acquiring analytical capabilities with multiple instruments of almost all of them. The RBS lab is located in Sunnyvale, California. The lab has 2 tandem linear particle accelerators running alpha particles. Before diving into the SMART chart, I want to give a brief review of precision and accuracy. Our goal can be likened to the objective of hitting the center target. The closer the target, the more accurate, the better. Precision also can be likened to reproducibility. Again, the more precise, the better. Most techniques fall in somewhere between or into one or other category of providing higher accuracy and higher precision and lower accuracy, or vice versa, lower precision and higher accuracy. Where does RBS stand? Well, RBS is a technique that can be thought of as accurate. Now, as for precision, the precision depends generally on the elements being analyzed. It can be very precise in some cases and not too precise in others. This chart is a spectroscopy and microscopy analysis resolution tool, or SMART for short. This chart is somewhat famous and was previously known as the bubble chart. Each of the bubbles represents a different analysis technique. The surface analysis techniques are inside the box. Outside the box on the right, we have bulk techniques. These techniques have a range of detection limits, but do not provide information regarding depth. Below the box are the imaging techniques. These can measure surface properties and features of various sizes, but do not provide chemical or compositional information. The last feature I'd like to point out is the color of the chart. The bubbles are color-coded to indicate the type of information that each technique provides. Looking inside the box of surface analysis techniques, the blue bubbles, such as RBS, which I will discuss this morning, show techniques that provide atomic composition. The red bubbles provide information on molecular bonding or oxidation states. The RBS blue bubble, of course, is in the upper right-hand corner of this chart. This figure shows approximately the measurement depth of various techniques. As can be seen from the chart, the idea of a surface analysis has a somewhat different meaning depending on the technique being used. RBS is located in the middle of the chart, right here. For RBS, the measurement depth is typically the top about micron or so of a sample film. Now let us begin our discussion on RBS and accelerator-based techniques. The accelerator-based techniques include RBS, HFS, ion channeling, and NRA. RBS stands for Rutherford backscattering spectrometry. HFS stands for hydrogen forward scattering. NRA stands for nuclear reaction analysis. The accelerator techniques are based on collisions between atomic nuclei, and RBS derives its name from the physicist Ernest Rutherford, who was among the first scientists to pioneer the concept of atoms being composed of nuclei surrounded by electrons. The analytical techniques of RBS, HFS, channeling, and NRA are used in concert to provide the broadest view of a sample. Now, the ideal RBS sample has all the features of interest, isolated and background free. This is rarely possible in real films. Thus, approaches such as HFS, channeling, and NRA are used to overcome the intrinsic difficulties in RBS analysis. Due to the wide diversity of samples and substrates, the analytical strategy is often customized to each particular film and film substrate pair. Okay. The primary, hang on a second. The primary applications of RBS and the accelerator-based techniques are as follows. Determine quantitatively the elemental composition and thickness of thin films or thin film structures. To determine the film density, given a known film thickness, and vice versa. We can determine the film thickness given a known density. Measure the concentration of hydrogen in a film. RBS is unique among techniques in being able to measure hydrogen content. The other technique that can do this is SIMS. Finally, being an ion beam technique, RBS can be used to evaluate crystalline damage in thin films as a result of processing, as well as provide information on dopants, impurities, and defect densities. Analytical problems have many facets, and sometimes choosing the right path to analysis can be challenging and difficult. Due to the multiple information paths available to us, RBS may help define a problem and an analytical strategy. It is a good choice for an initial analysis of thin films for both comparison or reference measurements. A first stop with RBS may save time or money in the long run. Accelerator techniques, that is RBS, channeling, HFS, and NRA, are important for the development of references for other techniques. Many different types of materials have been successfully analyzed with accelerator techniques. The films and materials shown in the upcoming sections of this presentation are only a portion of the materials that can be studied. Now on to a brief description of the equipment used in an RBS measurement. The accelerator consists of an ion source, a high voltage terminal, a series of electrostatic lenses and switching magnets, and finally the analytical chamber or end station. The sample is mounted on a multi-axis goniometer stage inside the end station. The system and the sample are under a vacuum of approximately 10 to the minus 7 pascals, about high vacuum. Now, this is a summary of the process of beam generation. Beginning with garden variety helium gas. Helium is electronically excited into a plasma. The helium plasma is passed over a charge exchange that consists of an oven that generates an alkali metal vapor, rubidium or lithium usually. The resulting ions are then injected into the high voltage terminal and accelerated to an energy of 2.2 MeV. The high energy alpha particles that exit from the terminal are selected by means of switching magnets and focused into a monoenergetic ion beam using the electrostatic lenses. The beam enters the sample chamber where the ions then collide with the nuclei in the target sample film. Backscattered ions from the nuclear collisions that take place with the sample matrix are detected by surface barrier detectors placed inside the chamber. Now, what does RBS measure? RBS measures the energy of helium, the energies and the yields of the backscattered particles from the atoms in the sample film or film structure. The energy of the backscattered helium atoms depends on the mass and the depth of the target atoms. This can be related to the kinetic scattering equations and the stopping power of ions in matter. The yield, or number of backscattered ions, depends on the atomic size and the concentration of the element, and can be related to the scattering cross-sections of the elements. In the next slide, we will see how RBS is able to obtain depth information. So let us begin with this picture. In this picture, M1 is the alpha particle, the helium nucleus. The box on the left represents the sample. M2 is the target atom within the sample. M1 penetrates the sample matrix and encounters M2 colliding with it. It backscatters out of the sample. How is RBS able to obtain depth information? The way it does this is the final energy of a backscattered particle is equal to the sum of the incident energy of the ion minus the energy loss due to momentum transfer to the target nucleus, and also minus the energy losses that the particle undergoes after passing through the sample matrix. The collision is Coulombic in nature. I'm referring to the Coulombic force that always is present between any two nuclei, but this can be modeled as an elastic collision using classical kinematic equations. The energy of a backscattered particle detected at a given angle depends on two processes: the energy loss due to transfer of momentum to the target atom during collision, and the energy of transmission through the sample matrix, both before and after the collision. Now, let us begin with the case of no energy loss due to transmission through a matrix, just atoms of different masses and sizes at the surface of the sample only, in the next slide. This plot shows the response of various representative atoms having different atomic numbers and therefore different masses and sizes to an incident particle beam colliding with them at the surface. Okay. The horizontal axis is the backscattered particle energy, and the vertical axis is the number of counts or intensity of the signal at that energy. To reiterate, all atoms in this plot are assumed to be at the surface of the sample before we hit them with the ions. Now, the more massive the target atom, the greater the backscattered energy. We can follow this trend down to nitrogen. Also, the more massive the target atom, the greater the yield. This is due to the fact that in general, higher Z nuclei are also larger in size and therefore present a larger cross-sectional area to hit. We can follow this trend down to nitrogen. The essential quantitative relationships between the backscattered energy, that's ESCAT, vary with mass, and let's see, and also the scattering cross sections with atomic number, that's denoted by Z, are shown above. They are simplified from the actual equations of elastic kinematics and scattering cross sections, which are more involved. And so these simplified forms are easier to show here. Now, note that for the purposes of this presentation, the cross-section relationship, sigma relative, is written in reference to the heaviest atom in this example, bismuth. Also, the kinetic relationship is written in reference to the kinematic collision between the target atom and the incident ions, the helium nuclei, which have a mass of 4 AMU. Okay, some observations. Scattering cross sections are proportional to the square of the atomic number Z. As a consequence, there are greater backscatter yields for heavier elements. So detection limits improve significantly with increasing mass. There is an approximately 2 orders of magnitude difference between the in yield between, and therefore the sensitivity, between the lighter elements and the heaviest elements of the periodic table. However, mass specificity, the ability to separate one atom or one element from another, decreases with increasing Z. In practical terms, this means that having a priori information about the elements expected to be in the sample is necessary for proper quantification. The next slide is our first example of an RBS spectrum. A platinum metal film of thickness about 1,000 angstroms deposited on silicon. Okay, this is an example of an RBS spectrum. The horizontal axis is the backscattered energy, and the vertical axis is the yield of backscattered particles at that energy. The horizontal axis unit, channel, is in reference to the multi-channel analyzer hardware used to perform these counting statistics and the sorting out of the particles' energies. The sample is a 1,000 angstrom platinum metal film deposited on silicon. Since this is a simple film, there are only 2 features on this spectrum. The platinum feature is blue and the silicon feature is yellow. Now, only a thin layer of platinum atoms are at the surface. The rest of the platinum and all of the silicon are buried at depth. Those surface platinum atoms are here at the highest backscattered energy. As the ion beam penetrates the sample, the ions encounter and bounce off more atoms at depth with progressively lowered backscattered energy. Thus, the bulk of the platinum film is revealed down to the interface between the platinum and the silicon. Next up is silicon from the silicon substrate, and this continues on down towards 0 energy. I should mention that in RBS, we always read a spectrum from right to left. We always read a spectrum from right to left. The yields, or relative heights of platinum and silicon, reflect the differences in the atomic sizes between platinum and silicon. If no platinum film were present at all on this sample, and we were just looking at the silicon substrate only, remember, no platinum film, then there would be no blue peak here, and the yellow peak would be shifted to the position indicated on the graph. That's here. Sometimes multiple RBS spectra are needed to unambiguously determine a thin film structure, and that is the subject of the next slide. Okay. The sample stage is placed in the path of the ion beam and oriented to be normal to the incident ions. The location of the detectors is significant. One detector is placed at as close to 180 degrees or full backscatter as possible. Of course, we cannot place it directly in the path of the beam or we'll be blocking the incident ions. So 160 degrees relative to the incident beam. The other detector is placed at a grazing angle in the range of 100 to 115 degrees to optimize the resolution of spectral features as needed for the elemental structural analysis. The RBS spectra from the two detectors are simultaneously acquired during the same acquisition. Once we have acquired the data, we need to fit this data to a structural model of the film. The process begins with an initial guess, then is successively improved. Fitting the data includes satisfying multiple spectra and is an iterative process to achieve self-consistency. RBS fitting does require some a priori information about the elements in the film structure prior to starting the analysis. The next slide shows an RBS fit of a thin film using two spectra, one at 160 degrees and the other at a grazing of about 92 degrees. The film is a 50 angstrom chrome silicide on silicon substrate. Two spectra are shown, 160 degrees. This comes from the normal 160 degree detector, this top plot, and 92 degrees. That's the bottom. The length of travel, the path of travel of backscattered ions. The length of the path of travel of backscattered ions going to the 92 degree grazing detector is a longer path. Thus, the energy loss by these ions is greater. This leads to an amplified spectral peak width of the silicon feature in the grazing spectrum. That's here, and also the chrome spectrum, chrome feature as well. The advantage of acquiring additional spectra is that it enables us to resolve ambiguities from data acquired only at a single angle. This difference can be used to optimize the depth resolution and quantification of the elemental ratio of the elements in the film. The next example is RBS depth profiling of a multi-layer tungsten silicide film stack. So here's the example. The film structure is about 2,000 angstroms tungsten silicide deposited on top of 1,100 angstroms of polysilicon, then a layer of 1,000 angstrom silicon oxide, finally the silicon substrate. The tungsten silicide top layer has a composition gradient as seen in the RBS data. On the left are shown the two spectra, 160 degrees in the top and 110 degrees. On the right is just a graphical representation of the structural model used to fit the data. For the purpose of this presentation, the interfaces are exaggerated to allow us to better distinguish the elemental lines from each other. The actual data and the fits are on this side. Note the tungsten and silicon features. There is a gradient as seen in the data. The tungsten silicide film is enriched in tungsten at the interface with the underlying polysilicon layer. The tungsten silicide layer is therefore fit by breaking this feature into 3 layers. The gist of this is this. When a gradient is detected in a film, then the film is modeled with 2 or more layers. The multi-structural model, the multi-layer structural model, is meant to be a representation of the actual composition gradient in the film to within the limits of RBS depth resolution. Typically, for film structures of this kind, the RBS depth resolution is about 10 to 15 nanometers. 10 to 15 nanometers. The next slide is a comparison of 3 films with varying composition of elemental ratio. This slide presents an overlay of the RBS spectra of three films. It's an overlay of 3 sample films of tungsten silicide on silicon. They vary in composition by their tungsten and corresponding silicon content. The 3 films in this plot are labeled by their SIW ratio or silicon tungsten ratio. For clarity, just the data, not the fits, are shown. We can readily distinguish and fit each spectrum and quantify the differences in the elemental ratio. The tungsten peaks for the 3 films are well separated from the other peaks. And each of the 3 silicon peaks forms an easily resolvable step that can be quantified. There's also an impurity in these tungsten silicide films, argon, which is detected. One more example for RBS follows, then we'll proceed to HFS. This is an example of RBS of a thin film on a carbon-based substrate, polyethylene. This slide shows the RBS spectra of fluorine and oxygen surface residue on polyethylene. The F and O peaks are well separated from the carbon-based substrate and from each other. They are magnified 25 times in this plot for better presentation and visibility. The areal densities of the fluorine and oxygen are measured to be on the order of 10 to the 15 atoms per square centimeter. This would correspond roughly to a film of approximately 15 to 20 angstroms thick. 15 to 20 angstroms thick. This type of precision is possible only when the elemental peaks are well separated from each other and from the substrate, which is carbon in this case. Let us now look at the process of making hydrogen measurements. Okay, HFS. HFS, as a reminder, stands for hydrogen forward scattering. This slide shows the analytical configuration for HFS. The geometry setup differs from RBS. The sample is rotated so that helium ions now collide with the sample at an oblique angle, about 30 degrees, which allows particles to scatter forward into the detector. Both alpha particles and hydrogen from the film are scattered forward, so a foil made of aluminum or polyethylene is placed in front of the detector to prevent alpha particles from reaching the detector. Only hydrogen is counted by the detector. Hydrogen still passes through because the foil is not thick enough to stop hydrogen nuclei. Only a small represented amount of hydrogen is lost by the sample in most cases. Only in the most fragile films, mainly low-K dielectrics, for example, only in these films does H loss from the sample due to the ion beam become an issue. We mitigate this issue by reducing the beam current or acquiring a series of lower doses at several regions on the sample. In the literature, this technique is also known as ERD, elastic recoil detection. So HFS is a form of ERD. It is actually a restricted form of elastic recoil detection analysis in that the only element which can be forward scattered from incident helium ions is hydrogen or deuterium. This simplifies the experimental arrangement and allows the analysis to be optimized for accurate hydrogen quantification. The next slide shows an HFS spectrum. The HFS spectrum is seen on the right. In this example, it is combined with the RBS data to obtain the total elemental composition of the film, silicon, nitrogen, and hydrogen. There is a degraded resolution compared to RBS that can be observed. This is due mainly to the use of the foil to stop alpha particles, and also just the inherent nature of the extreme glancing angle that must be necessarily used. It is just more sensitive to minute variations in the geometry at this angle. Some examples of films analyzed by HFS, though, are silicon nitride, silicon oxide, silicon oxyfluoride, silicon carbide, and carbon, and many others. All may contain considerable amounts of H. Determining the total composition and the effects of any annealing steps often requires both an RBS and an HFS measurement. In the next slide, we will discuss channeling and NRA briefly. As an ion beam technique, RBS can be used to perform channeling experiments. The incident beam is aligned parallel to a major crystallographic axis in this sample. Interactions of the incident ions with atoms on the crystal lattice steer ions into the main axis channels. The scattering yield is significantly reduced for ions on lattice sites, and amorphous and damaged regions of the crystal can be observed and measured. RBS can be used to determine damage profiles, dopant substitutionality or interstitiality, epitaxial quality, and gross damage or amorphization. This can provide valuable insight into the behavior of impurity atoms in single crystal materials. Some examples of materials include both pure and doped crystalline silicon, silicon carbide, germanium, and gallium nitride. In NRA, or nuclear reaction analysis, the incident ions, such as helium or hydrogen, impact the target atoms with sufficient energy to overcome repulsive electrical forces, allowing the incident particles to interact with nucleons in the target matrix. A short-lived excited nucleus is formed. This compound nucleus decays, releasing energetic photons or gamma rays and or energetic particles, leaving a residual nucleus behind. NRA can be useful for extending the lighter element quantification. Let's look at a couple examples of channeling in NRA. This is an example of a channeling study on an implant anneal system and antimony implanted silicon sample. The channeled spectra were acquired from the as deposited implanted sample and compared with the annealed sample. The overlay of these two spectra is shown here. A comparison of the two channeled spectra shows clearly amorphization during the implant, that's light blue, and regrowth of the silicon crystal after annealing in red. Channeling yields information about the thickness and damage in the implanted zone and the effects of annealing on the crystal structure. Now to the NRA example. This is an RBS plus NRA measurement of a boron silicide film. The NRA spectrum is on the right side. Generally, NRA measurements are planned so that the more energetic or penetrative reaction product can be counted in a background-free condition. The reaction used here is a boron-10 alpha-P carbon reaction in which alpha particles collide with a boron-10 isotope to release exothermic protons and residual carbon nuclei. The proton yields were used to quantify the boron. We now come to a summary of the strengths and limitations of RBS. The strengths are that it is quantitative without standards, with reproducibility to somewhere between 3 to 8%. The method is non-destructive. RBS can provide depth profile information. RBS can analyze all elements, including hydrogen, and it can analyze insulators and conductors. In addition, there are no sputtering artifacts, since RBS is not a sputtering technique. The accuracy is dependent on the equivalence of substrates, not the sample matrices. Now, to what are some of the limitations of RBS? Well, it's a rather large analysis area. The beam spot is a rather fat 1 to 2 millimeters. The maximum measurement depth is about 1 micron or so. Beyond this depth, the ions tend to scatter and therefore generate greater uncertainty. The minimum sampling depth or depth resolution of RBS is about 5 nanometers or 50 angstroms. And finally, RBS does have relatively poor detection limits for light elements. So this would affect samples containing low concentrations of light elemental impurities. To mitigate this, EAG has a host of techniques available to complement the limitations of any one measurement. For RBS, the techniques of SIMS, XPS, OJ, and XRF are good complementary techniques. So I would like to include 2 final examples of this, RBS and SIMS and RBS and XRF. So here's an example of an RBS and SIMS combined analysis of a silicon nitride film containing a low-level impurity, low-level light element impurity, oxygen. From the RBS spectrum, we are able to determine the silicon nitride elemental ratio of the film accurately and precisely. In this film, the concentration of O that is present is below the detection limit for RBS. O present would be about here. The concentration is about 1 atomic percent. SIMS is able to detect this O concentration and quantify it after calibration with the RBS results. Here's an example of RBS and XRF. This film contains 2 elements of similar mass, strontium and zirconium, in addition to other elements, barium, tantalum, and oxygen. RBS can determine the sum of the 2 elements, strontium and zirconium, but cannot resolve them individually. The 2 peaks overlap with each other severely to the point where you cannot resolve them. As the strontium and zirconium cannot be mass resolved by RBS, wavelength dispersive XRF is used to determine the elemental ratio of these 2 elements. The information about the strontium-zirconium ratio is incorporated into the RBS model, and the total composition of the structure, including all of the elements present in the film, is determined. These are just the most common complementary techniques done in combination with RBS to achieve composition analysis. Here we go. For improved surface sensitivity, detection limits, or depth resolution, RBS is often combined with XPS, OJ, or SIMS. For films containing elements of similar mass that cannot be resolved, RBS is often combined with wavelength dispersive X-ray fluorescence, XRF. We'll continue this SmartChart webinar series over the next several weeks to explore more of these techniques. So why choose EAG? I think, well, let's see. There are several reasons, but I think it's important to state from the beginning that client confidentiality is core to our business. We are a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. Finally, in light of the pandemic that is affecting all of us right now, I would like to stress that EAG Laboratories is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID-19 regulations from state and local governments, as well as the Center for Disease Control. Currently, all of our locations throughout the world remain open, but we may have limitations on customer visits. As this continues to be a fluid situation where we are operating a laboratory at reduced capacity, we can also transfer your samples to another EAG location. We encourage you to discuss your options with our sales representative. Here's a schedule of the upcoming webinars. These webinars will cover SIMS, organic techniques, surface analysis, and more. Thank you for listening to this webinar on RBS.
Thank you, Daniel.
Thank you.
As Daniel mentioned, we do have some upcoming webinars. We have one tomorrow on SIMS. In the chat window, I did include registration links for the two upcoming ones, SIMS and FTIR and Raman. At this point, we're now going to begin answering the questions submitted during today's presentation. Venkat Vemuri, scientist at EAG Laboratories, will be joining us as our moderator during the Q&A session. As a reminder, you can still submit questions through the questions panel in the bottom right of your screen.
Hi, this is Venkat Vemuri. Here we have many questions being asked by the attendees. I would, within the limit of the time limitation we have, I will ask, we can answer as many questions as possible. Here, the first question starts with, what is the depth resolution of RBS? Daniel?
The depth resolution is about 5 nanometers. It will vary, of course, with the structure of the film or film stack. If it's a film stack and there are overlaps, I would say the depth resolution would increase to somewhat more, 10 to 15 nanometers or so. The depth resolution of, I think I showed a slide in which the film is very thin, 50 angstroms. Yeah, that is probably about the limit of depth resolution of the technique. So, yeah.
And another question is highly specific to the sample thickness. What is the range of the samples, like thickness, the lowest and highest that RBS can measure?
Lowest, well, let's see. I would say the absolute thinnest thickness. Generally, I would say it's, in a more practical sense, probably 100, 150 angstroms. Obviously, we can go thinner than that, but that depends, of course, on the conditions of the and the substrate used. As far as the lower limit would say, for most practical instances, it was 10 to 15 nanometers, but we can't go lower than that. The maximum thickness is about, I would say, a micron to a micron. About a micron is for the majority of films, but we can go much thicker. We can go as deep as 2 microns, maybe. Yeah, 2 microns. It depends on the type of film and its thickness, and also the substrate used. So somewhere between, so in conclusion, I would say somewhere between 100 to 150 angstroms and 15,000 angstroms.
Okay. And another question here we have is, can RBS resolve the elements of similar Z numbers? So for example, the elements, those are close to each other in the periodic table.
Yeah, that's a good question. The short answer is no. RBS alone would have difficulty resolving elements that are very close in mass. And for that, we usually turn to elements that are close in mass. Typically are transition metals. Transition metals such as cobalt, nickel, copper, for example, iron, cobalt, maybe, or cadmium, tin, something like that. For that, we often call on an additional technique to use here. You know, one of the complementary techniques I mentioned was wavelength dispersive X-ray fluorescence, or WDXRF, which has the ability to resolve these elements. So for films that contain elements of similar mass, we often we often suggest the use of a combined RBS plus XRF technique for this type of analysis. And we have methodologies in place for doing this. So
okay. And another question is we have here is, does RBS cover a ppm level detection for all the elements or few elements? So what it can detect in ppm level, or what else we can do with this?
Mm-hmm. The heaviest elements certainly can be quantified in ppm terms. We're talking about elements like tungsten, gold, lead, bismuth, platinum. Coming down, maybe going further up, tellurium also, I think, and antimony. It depends on how able we are to achieve a background-free condition. If the film is well separated, if the film elements are well separated from each other, for example, tantalum nitride, for example, then we can achieve ppm levels. Also, if the substrate is lighter than the elements present in the film, then there's a good chance we can achieve ppm levels also. ppm levels tend, they're also dependent on the scattering cross sections of the elements. Therefore, it's the higher Z elements that can achieve ppm. The lower Z elements are possible, but only under certain conditions, such as a lighter substrate or thinness of the film.
I would like to extend a little bit on this question. And SIMS can measure ppm level, and if we complement RBS with SIMS, we can measure the matrix elements as accurately as possible. Then SIMS can measure ppm level contaminants or ppm level dopants more accurately if they have very accurate matrix information from the RBS. So we can complement RBS technique with SIMS, and which is a very powerful combination which we use for a lot of the clients, right?
That's correct. Yes, that's right. That's right.
And the NRA is able to detect all dopants or only limited ones. So can NRA be used for everything or only for few dopants?
Only a few, and generally restricted to lighter elements. That's where they find the most use, the most application. The NRA is used mainly to extend the detection limits of lighter elements for a certain concentration range present in the film, usually on the order of 2 or 3 atomic percent to less than 10 atomic percent. The elements I'm talking about are elements like boron and lithium. Those are the two main ones, and to a lesser extent, carbon, nitrogen, and oxygen.
Okay. So what is the minimum detection limit for hydrogen in HFS?
Well, it's very good. The detection limit is something like 0.1 or 0.2 atomic percent. Yes. It's quite sensitive.
Quite sensitive, yes. How accurate is the depth resolution for RBS?
Yeah, how accurate is the depth resolution? In other words, is the concentration what it is in the depth resolution? Well, I'm trying to figure out how to explain this one. It is how accurate it is. It is accurate to the depth. The films are accurate to within the depth resolution. The concentration are accurate to within the depth resolution that we can resolve for a spectrum.
Okay. And there is another question, that is what software or program the data analysis for RBS we use. This I will elaborate more by myself. And here at EAG, we have our own proprietary software that is poised to analyze high throughput data analysis more accurately. So we have our own software called Rubicon. There are other software packages such as RUMP and the Weninars available in the open in the community, but we have our own software that we use for data analysis. So I think that
Yes, that's
answers.
right. Yes, we have our own in-house developed software.
Yeah,
It's you might call it, one could call it a canned version of a rather seminal program from a long time ago, one called Hypra.
and now it is Rubicon, like, so it is upgraded and all this thing. And also one more thing I want to mention is we have a custom design end station that is not that is poised or designed for high throughput data analysis. So the advantage at RBS, doing RBS at EAG is we can match the speedy requirements of the clients, and so we have everything is optimized for high throughput data analysis and high throughput speedy data delivery. So if we have rush jobs and all those things, we can do that.
Yes, that's right. Yes.
And another question is, how does the detection limit of RBS compare to SIMS?
SIMS is definitely the more sensitive technique. When greater sensitivity, parts per million and parts per billion are required, SIMS is the correct choice for that detection. Yes.
Yeah, if we complement RBS HFS with SIMS, we can get very valuable information for the films. Like we give as accurately as possible for the matrix composition. From there, SIMS may build accuracy in the PPB or PPM level information. So I think there are a lot of other questions. I think for today we have I see we have answered almost all the questions.
Excellent. Excellent.
There are other specific questions related to the equipment market. Those somebody will follow up with those kind of questions. So for today, we are concluding the Q&A session. So I think sorry. There is another question, Daniel. Like, is it possible to analyze bulk samples?
That's a good question. Yes, under some circumstances. It's not the ideal technique for all bulk substances, but for certain ones, yes. Mainly, I'm talking about bulk substances where the elements present in the film are well separated. For example, to pick an easy one, aluminum oxide, for example. If we had a piece of aluminum oxide or silicon oxide, if we put a piece of glass, pure glass, under the beam, we would be able to determine the concentration of that glass. We would have to qualify it, or there's a caveat, of course, because the maximum measurement depth is about a micron or so. So the composition is accurate in that top micron of the sample. Below that, of course, we don't know for sure, but if it is known that this substance is pure, known to be uniform in composition, then the measurement is certainly representative of the entire sample.
Okay.
So yes.
And yeah, we can do. And there is another latest question. What effects would sample surface roughness and electrostatic charging have on measurement and analysis?
surface roughness and electrostatic charging. Oh yes,
Yeah.
what effect on analysis? Roughness, if the film is extremely rough, then we will see, of course, is the presentation of multiple surfaces to the beam. That will introduce a bit of scatter into the spectra. What the ultimate effect is that we probably will see, rather than the nice tall vertical peaks in the spectra, we'll see something like trapezoidal type shaped peaks. The depth resolution then suffers a bit. Yes, it suffers to the degree of the roughness. But otherwise, in terms of the actual composition, if we're talking about a uniform film, actually that is not affected at all.
Okay.
As far as electrostatic effects, the system is basically almost unaffected by charging issues. We will experience some charging if, say, we hit a piece of glass, for example, with the ion beam. We do introduce some charge, but we do have ways of mitigating this issue by surrounding the area of acquisition with conductive material, and that almost always actually mitigates the charging effect. So we essentially don't suffer from charging effects. Insulators or conductors, we were able to measure both.
Okay. And also for today, I'll take one more last question. And there is another question that is, what makes RBS an accurate thin film characterization technique?
Good question. I have a very good answer for that. It's the fact that it is a standardless technique. It does not rely on standards or calibration standards to quantify the composition. What it does rely on are the fundamental physical constants of scattering cross sections and stopping powers, and of course our knowledge of the masses and isotopes of the chemical elements, and that's it. Otherwise, it's the equations of physics that
Yes,
we're relying upon here.
something similar to like a first principles solution of the data
Yes.
that solves the physics of the sample to give us the composition, right?
Yes, that is correct. Yeah, and that is the overriding strength of RBS.
Okay, so that concludes the question and answer session. If there are any more questions the clients may have, you may contact us.
Yes,
or
please feel free.
Please feel free to do that. Rena?
Thank you. Yep, thank you very much. Thank you, Daniel and Venkat, and thank you everyone for attending today's webinar on RBS. If we didn't get to your questions today, we'll be following up with you soon. If you have any other questions, please send in your questions to the email address on the screen. Once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate if you would complete the survey and provide your feedback. Please be sure to register for our upcoming webinars in the series. And on behalf of EAG Laboratories, a Eurofins company, and our presenters, thank you for joining us today and have a great rest of your day.